The overall goal of this procedure is to demonstrate the utility of simple Millifluidics-based lab-on-a-chip devices for high-throughput synthesis of nanomaterials, time-resolved investigation of their formation, and demonstration of continuous flow catalysis. This is accomplished by first demonstrating the synthesis of copper nanoparticles using a millifluidic reactor. Next, the formation of gold particles within the millifluidic channel is visualized using time-resolved in situ X-ray absorption spectroscopy in order to observe reaction intermediates. In the final part, continuous flow catalysis is demonstrated by the conversion of 4-nitrophenol to 4-aminophenol as it is flowed over gold nanostructures within the millifluidic chip. Ultimately, these three experiments demonstrate that simple millifluidic systems offer opportunities for high-throughput synthesis, in situ investigation of formation, and carrying out continuous flow catalysis.
The main advantage of this technique over existing methods like traditional microfluidics is that they can accommodate higher flow rates due to wider channels without compromising on fluid properties. They also enable easier scale-up of reactant volumes for larger scale synthesis, and they provide an effective platform for probing reactions in situ using different spectroscopy tools.
This method can help answer key questions in the field of flow-based devices such as real-time in situ monitoring of chemical reactions, mapping the growth of nanoparticles, and kinetics of a catalytic reaction.
For those researchers who are not familiar with lab-on-a-chip devices, these experiments at first may seem a little complicated, but once they get familiarized, these are pretty easy to carry out and can be applied easily to their own unique investigation.